First slide. Yes. Good afternoon. So today we will discuss mainly electron microscopes and atomic force microscopes. So far we have discussed about different X-ray based techniques like diffraction and scattering techniques and neutron diffraction as well, X-ray diffraction and all small angle and small angle neutron and X-ray scatterings. So today we will discuss about electron microscope and atomic force microscope. First, coming into electron microscope, so why do you need an electron microscope? The first things, because you see, there are many optical microscopes are available, but in optical microscope we have many problems that many drawbacks, or we can't see many things. So we have to go for an electron microscope. So electron have much shorter wavelength than that of that have visible light, and thus allows sorry, there was some technical error. So first of all, why we need an electron microscope? All of us know the electron have much shorter wavelength. That wavelength in the range of like 0.002 nanometer in case of TM, very low wavelength, very small wavelength than that of visible light, and allows electron microscope to produce high resolution images than compared to standard light microscope. If you see the wavelength of visible light, that is about lambda of visible light is 400 to 800 nanometer, but that comparison to lambda of an SCTM transmission electron microscope about 0.0025 or 2 nanometer is much smaller, and because of that it produces very high resolution image can be produced. And electrons have strongest interaction. If you see the interaction of electron beam with matter and interaction of visible light with matter, that there is a drastic difference between them. So electron have stronger interaction with the matter of any radiation, and so many types of information can be possible in that case. And third thing, it has high intensity, high energy. Beams of electrons are accelerated, easy to generate. So it's a production of this electron beam of high intensity and high energy is possible, and it used in conjunction with a variety of the ancillary technique like thin sectioning, immunolabeling, negative staining, some of the examples. So electron microscope we use because it has a very shorter wavelength, so we can go for high resolution, and that it interact with very interaction is strongest as compared to optical lights. So that's why we get much more information. Okay, so that's why we need that lambda. If you see this depending upon the energy, it's varying 0.0022 to zero point 0.1 nanometer, such a small one. If you see that how this, we just recalling that how that electron beam interacts with the matter, as you know, we'll go to a SEM or a TM, that is scanning electron microscope or transmission electron microscope. All those electron microscope, depends on the interaction. How does the electron beam interact with the matter? If you see, when electron beam strikes the sample, a large number of electron and photon signals are generated. If you can see here, this is the electron beam. It interacts with the interaction volume that we discussed already. From the interaction volume on the top surface, we have a secondary electron, that is nothing but is a photoelectric effect through electron is come up. The energy is between 10 to 15 electron volt, and you have a backscatter electron, that is the same electron is coming back after interacting with the matter, with the sample, that is backscatter electron. See, both secondary electron and backscatter electron, these two electrons are used in the principle of scanning electron microscope. And then during the interaction of electron beam, that there are some X-rays are produced, and that X-ray are used for X-ray mapping. In case of SEM of TM, all we know that EDAX analysis, energy dispersive X-ray analysis, for compositional structure to find out the composition or elemental mapping, we do that X-ray we use. Then there is an Auger electron is produced that can be used for the Auger electron spectroscopy, that we will discuss in next class, Auger electron spectroscopy. And whatever the transmitted beam is passing through the matter, that will give you transmitted electron, that is used for transmission electron microscope. And then there is some luminescence, that's cathodoluminescence, that can also be detected. So on an average, if you see that SEM and TM based on the interaction of electron with the sample surface, whether it is backscattered or secondary electron in case of SEM, whether it is transmitted in case of transmitted electron microscope. Now coming to scanning electron microscope. So as the name suggests, you can see the term scanning is coming. That means that electron microscope, here we have a raster scanner. That scanner is, if you have a sample is like this, then your scanner is scanning on the surface from one X and Y position. So it gives a whole image. And how will it scan? That will display whole image. It divide into multiple matrix, like lots of pixels, small pixel. It scan individual, and then you sum up to get an electron microscope. If you see, a scanning electron microscope is a type of electron microscope that produce image of sample by scanning. That is a raster scanner, scan pattern by scanning the surface of the surface. If a sample, it will scan on the surface of the sample by one and two on the focus through the electron beams. So electron here interact with the atoms of the sample. As you know, the sample is composed of unit cell. In the unit cell, a lot of crystal. In the crystal, you have a unit cell. In the unit cell, there are a lot of atoms. This electron interact the atom, producing various signals that contain information about its surface. Mainly, it gives topological or topographic image. So if you see the historical background, the SEM was first built by Dr. Noll by Germany, and then Jockrid in USA. So it becomes practical reality by Professor Sir Charles Oatley Labs in Cambridge in 1950, and the concept is now much mature, but progress continues undebated. So it is continuously, it's more, this is the first SEM image. If you see, it is a size of a big room. So now if you see the current SEM, it's just a tabletop microscope. So progress is still going on, but overall it depends upon the scanning, how does the surface is scanned by a raster scanner. So if you see the information what you get, we mainly get four information. One is your topographic information. That means you see one that is surface feature. How does an object looks like? You can see this is a sample of a same as a barium titanate sample. You can see the 220 micron scale, and this is a 4 micron scale. You can see how the topography looks like. in 20 micron you can see a smooth surface just, but if you go to 4 micron scale, you can see how this the hexagonal type this this hexagonal type barium titanate samples are visible here, and different grains you can see, different grains are there, they are clearly visible. So topographic information it gives, that means how does sample looks like, a relation between these features and the material characteristic that will give. And second thing, it gives morphology, that shape and size of the particle. If you can see, if you see this is my grain, so this is my grain size, so that information will give that surface shape and size of the object relation to this structure and feature in the between relation between these features and material characteristic. So that will give you morphology. Then you can also get a composition analysis, that EDAX facility. You can use the electron X-ray imaging facility, EDAX, where you can see that composition, what is the element and compounds present in the sample, that you can see. In addition, you can also get crystallographic information, like you have a SEM that is called, that can also attach with specific oriented microscopy, that technique, that is software, with the help of software you can calculate, find out the crystallographic information, how does the atoms are arranged, relation, that relationship between the arrangement of atoms with the properties. So all those major 4 type of information you will get from a scanning electron microscope. You see the magnification you can raise from 15x to 2 lakhs is the up to magnification you can go. You can resolution is much higher, resolution 50 angstrom, and it's the depth of focus. If you see that sample to this electron beam distance, you have large depth of focus. You can vary the depth that quite large, up to 30 mm, 40 mm you can go that depth, and relative easy sample preparation. If you see the TEM and other technique comparison, SEM sample preparation is very easy. If you like, if you have a conducting sample, there is that means that you have a substance that can conduct electricity. So in that case, electricity here means electron beam is falling on the sample. It has to be passes through the sample to the ground. Otherwise, what will happen? You will get a surface will be, image will be broad. You will get white, only whitey noisy whitey signal. That is mainly due to the charging effect. So if you are conducting sample, little or no preparation is required. You can directly attach your sample with the brass top, like in SEM. You used to get a brass top like this type of strop. On that of the powder, you can directly disperse in acetone, and you drop cast here. Or otherwise, you can put your powder directly in double-sided tape, carbon tape is there. On that carbon tape, you can put your sample here. But you have to give, and this is the sample on the substrate, then you have to give a silver paste to the stage, sample stage, so that it will electron will, whatever the electron beam is falling on this, that will get a path to go to the earthing. Otherwise, what will happen? The charging effect will come into paste. So that's why the silver paint used to go to coat. But if you have a non-conducting sample, you have to prepare a thin layer coating of gold, carbon, or chromium. Like your sample is non-conducting, then you have to go for sputtering technique. Through sputtering technique, in a sputtered chamber, inside the sputtered chamber, you put your sample, and there is a gold substrate or carbon substrate on the top. Then you apply the arc current. What will happen? There will be sputtering will take place, and some gold atom will deposit on the sample surface. So it provide a conducting pathway. So sample stage can be, you can tilt it at so the beauty of this technique is now that you can tilt your sample to see for top surface, cross-sectional morphology, everything is possible here. If you can see, the wavelength can be varied from 0.1 to angstrom to 0.039 angstrom, depending upon the how much energy you are using, that whether 10 kV or 100 kV. So you have a tunability of electron wavelength here. So mostly we use most of the SEM-TM, they are using 30 to 40 kV. In general, their uses. And if you see the difference between the scanning electron microscope and the optical microscope, you can see that I've just given an example here. This is a SEM image that this is an SEM image and this is an optical image, optical microscope image. You can see here, you can just see the at 50 micron, you are able to see the grains. There are different grains are there, only grains. But if you see at 5 micron, you can go much beyond that. You will see the how that those grains are arranged, that hexagonal arrangement of the grains, that plate-like structure, growth steps, each and every growth step. So you are able to see in this. Similarly, in case of this radiolarion is a bacteria, this image of an bacteria that you can see here, that here the spikes are not visible, but in SEM with spike and internal feature you can able to see. So that means in SEM you can achieve a magnification much higher. You can go to up to 2 lakhs magnification. You can see the depth, field of depth of 30 mm much higher, and you have resolution about in nanometer range resolution. So such as high depth allows large amount of sample to be focused one time. So you can focus a large amount of sample, so you can get a good representation of three-dimensional structure you can get. And mainly optical microscope, low resolution and small depth of field. But you go to SEM, you are able to get large depth of field, and you can go up to high resolution to see the stacked layer, like I have the image I have shown here, or the spike. All those you can able to see. So that the imaging part you can see. But how the image design? If you see that image design, you can see that this is just an image I have shown, 3rd century mosaic structure. In this mosaic structure, you can see that there are small, that you can like grains. The small tiles are there, so they are arranged in the pictures in black, red, and all white, all those things. So similarly, like this is spots like the small this mosaic, like small parts you are seeing here. So how that the as electron beam when fall in the sample surface, it divide the whole image. Scanning occurs by pixel, like if you take a matrix like 512 matrix or 1024 matrix, so it will divide each whole image into small area, that is, those are called pixel, and scan individual area is that's pixel by pixel, and finally that you can combine them to get a image. So you can see here, this is the object. On the object, the scan, this is the scanning object, and then what happened that this is the scanning on the surface, like layer by layer or pixel by pixel, you will get a scan image on your computer. Mainly a synchronous raster scanner is there, and the once it scan, it amplify the signal and finally display on the image. You will able to see. So mainly if you see instrumentation part, the main thing is required is specimen. You have a sample specimen at the bottom of the here in the SEM microscope, and all the SEM microscope composed of mainly you have electron source, then different magnetic lenses are there. These are the anode, then these magnetic lenses are there, and then it fall on the sample surface. So if you see that the top electron sources, so that is mainly produce thermonic emission. By thermonic emission, electron will produce, and this electron will energetically attain high velocity by using different magnetic lenses before it focus into the sample surface. And you have a detector. The backscatter detector is the top of the sample, and side scatter detector, that is the secondary detector, is the nearby side, and you have a DAX detector, that is for composition analysis. So mainly if you see, you are using mainly 3 things. One is backscatter electrons, then there is a secondary electrons, and then fluorescence X-ray. So that backscatter electrons, the high energy that it gives you compositional contrast, it gives you the compositional contrast, and you have a low energy topographic contrast, that is the secondary electron microscope will give you topographic contrast, and then you have a composition analysis in the X-ray. You will use that for the composition of the sample. As I told, the electron beam source with a harmonic gun at the top of the electron, we have a harmonic source, that electron source where electron is produced. The electron is produced mainly the 2 types of electron source are used. One is a thermonic emission, another is a field emission source. So thermonic emission, there you have either tungsten filament or lab 6, lanthanum hexaboride or cerium hexaboride of crystal. You can see in case of lab 6 a pointed crystal used here, in case of here a tungsten filament. And this filament, when you heat it at a high voltage, and that the electron will generate, and then electron will passes through the lenses before it reaching to the sample surface. In case of field emission, here again that voltage difference, that potential difference is created, and through the potential difference that tungsten tips will produce to. Mostly that FEG field emission got source that use nowadays, that you can go up to high resolution SEM. The old conventional SEM, if you see, you can see up to 30-40 nanometer or beyond 100 nanometer, you can easily see. But you want to go to much lower than that, even 10 nanometer, you can able to see in FEG SEM. So SEM requires mainly high current density, that electrons per time per unit area, you need a high current density and a small electron spot. So the electron beam, if you focus, it has to sharp focus so that it can, it can scan on the surface very smoothly, and that pixel can be very, very small so that you can get better image. So if you see the optics of a scaling electron microscope in a conventional, in case of conventional normal microscope, like if you see, what you see is it's opposite image. You will see a magnified image, but that is opposite. The magnification equal to that D1. This is the distance here. D2 is distance here. The lenses to the subject plane. So D2 by D1 magnification. But in case of scanning electron microscope, what you will see from the aperture, once electron beam comes and fall on the sample surface, you will see the same image, not inverted image. Here in this case conventional, you are seeing inverted image. Here is the exact image you will able to see here, and then that here probe diameter will be such as the image diameter, that will decide that the magnification P equal to A by M. So A magnification is D2 by D1, so A equal to D1 by D2. Mainly it will give a direct image, no inverted image you will not get, and it depend upon the electron beam source, the energy of the electron beam, and that decides that how much that walking distance you will get to get a better quality image. So all these electron microscope must have a detector. So detector's job of detector is to detect that electron beam, how it that the electron is coming out, a second electron and backside electron, and then to generate that particular pulses or current, so that which can be converted into a 3D or 2D images. So if you see the backscatter electron, it mostly the sample, and backscatter electron is a circular electron just on the top of the sample surface. So electron energy of 30 to 50 keV. Images are more sensitive to chemical composition. Electron yield depends on that backscatter electron is mainly depends upon atomic number, jet contrast variable. So that means you have depending upon the composition of the substituent in the all the constituent of the your material, you will able to see their both composition analysis you can able to do by the using X-ray, as well as with the help of backscatter electron you can use the imaging structure. In secondary electron detector is line sight to the sample surface. You have a bias mesh, generally 100 to 300 voltage you applied here, needed in front. Once you electron is produced here, it has to come here. You have to apply certain voltage to come into it. Mostly it has a photomultiplier detector or a silicon scintillator detector, that semiconductor detector used in a secondary electron microscopes. So that is the detector part. Then when you see the image, you can see this is the image that you are seeing here at low 20 micron scale, and this is a 10 micron scale image, and the same image is 5 micron and 2.5 different magnification I have shown. So this is all different magnification. You are going to see internal features. You can see here, you can't predict what is the structure inside. Here you can see little information about how the circuit diagram of the is there. But if you see the much higher image, you can see there is a all there is contact is here, but in this one there is a break. That contact is break here. So those information of electrical circuit you can able to get, and similarly you can see here that magnification will be whatever the image in CRT, LCRT by L specimen. You can see the scanning on the sample here, then you are zooming the image, and hold the image on CRT is getting zoomed, and you are getting that magnified image. So as I told, in SCM, you have a focal plane, you have a large depth of profile. So you have a, you can, your field of depth, you can vary from 30 mm to 4.1 mm, that focusing depth can be vary. So based on the depth of field, the distance between the optical axis of either side, you can get a better image. SCM has large depth of focus field, which produce image that appears a 3D structure. You can see here, this is a secondary electron images, top image with 8 mm working distance, and below image that this image is 37 mm working distance, with both are in same micron scale. You can see how the features are able to see with varying the working distance. So by playing with the depth of the field, you can get a better image. Because just one example I have shown here, if you see the SEM image, an SEM image focused high magnification is a coil. In the coil that you can see that this is charging effect has to be there, that has to be nullified with gold or carbon coating. Once you have a proper coating, you can see the image. A 10x magnification, we can able to see only the ring structure, how these rings are aligned like an optical microscope. And if you go to 110x, I am magnified by 100 times, from 10x to 110x, you can see inside that one ring that I have this, if I take this particular coil, inside that coil, how my grains are arranged. You can see how densely arranged here, how big grains are there here in this lower part. So those things are able to get. So if you go to, again I magnified to 200x, you can see how these grains are precipitated, or that looks like inside the structure. You are getting more deeper information. If you go 400 micron, you can see all those internal features, the grains here, how their internal pores are there, all those porous structure. In 4000K, if you go to 4000K, you can see how this type of pore, that interconnected pores are there. These pores and these pores are interconnected. All those poral morphology you can see with a small void pot here. You can see, but you go to again has 16K, 16,000 magnification. You can see that void is, that small body is clearly visible in the structure. If you go to much higher, 45,000 x, you can see the void structure more clearly. So by varying the magnification of the electron ICM scanning electron microscope, you can able to see all internal morphology that is possible. But if you see, you have a both option, you have a secondary electron and you have a backscatter electron, both electrons are there and both can be used for imaging purpose. You can see here, this is a hair of a insect. There is a small crack inside this that is not visible in secondary electron. If you go to backscatter imaging, those, this is clearly visible here. And similarly, if you combine both a backscatter and a secondary electron, and you have only backscatter, you can see the broken structure with backscatter. Combining both, so you can getting both topographic and as well as morphological image. That means you have a backscatter electron that's giving compositional contrast, and you have a secondary electron that is topographic contrast, is giving topographic image, and you have fluorescent X-ray, you can get the composition analysis. All these are possible. So far I discussed the imaging part, but using the EDAX analysis, that this X-ray, the compositional analysis, that this X-ray, fluorescent X-ray that used in EDAX. So you can calculate, you can see the mapping structure. You can see this is a manganese dot zinc oxide sample. So I mapped that manganese K alpha and its cobalt cobalt K alpha. How it corresponds to each K alpha manganese, I am getting a dots here. So I can see here that the manganese is uniformly doped in zinc oxide. My cobalt is uniformly doped in zinc oxide with small, you can see here some cluster here, some cluster here. So mostly during this, that outer cell electron will jump when the secondary electron is produced at that time. So as you discussed that photonic reflect, that one electron beam is, the electron is coming here, this electron knockout, it create a hole, and that hole will fill by an higher orbital electron. So some X-ray will generate, and that X-ray will help you to get the fingerprint information. So elemental mapping up to 0.1 atom %, you can able to detect by scanning electron microscope using the EDAX facility. In addition to SEM, if you have we have an environmental SEM, that is ESEM, that is like, for example, you have a bacteria or virus sample and you are going to keep them in normal scanning electron microscope. There what happened, you have a vacuum and you have energy electron beam is much higher, like 30 to 40 kV. With such a high energy beam, your virus or bacteria can be disintegrate or can be damaged. So in order to see those bacterial image or virus samples, you need a environmental SEM that is mainly used for biological samples, a vacuum sensitive sample, the irradiation sensitivity sample where high energy is called damage, that you can thin organic films, or you have a wet sample, oily, greasy samples, or you have an insulating sample, they are used ESEM sample where the environment is controlled such a way they have a nitrogen atmosphere and the temperature is a little lower so that it will it retain the structure of the bacteria or virus. It is used to image chemical and physical processes like mechanical stress testing, oxidation of material, hydration, dehydration, like you have a paint coated on the sample surface, how the paint is getting dried, when the paint is getting dried, what are the internal morphology are changing, those information you can get by environmental SEM microscope. Here the pressure is much lower, 0.08 to 32 bar, and vacuum is also low, and various gases can be used to control the environment of the mostly argon and nitrogen used to provide an inert atmosphere. So mostly if you see the SEM is give you topological information and that is topographic information, that how does the surface looks like, and then you have a morphological information, that is shape and size. Then you have a composition analysis, you can see which elements are present and what is the percentage of each element that can be quantified in case of that using the X-ray produced during the electron interaction in SEM. Then also you can see the crystallographic information if you have a conjugated with a topographic particular oriented microscope that is conjugated with the focused ion beam, that is SEM with the FIB. That I am not discussing, focused ion beam, that mostly metallurgical sample they used to use that SEM with FIB facility, so you can get the crystallographic orientation, whether this orientation in which direction, and all those things you can get. So similarly with SEM, that use the scanning electron microscope, mostly the two electron, that secondary and bastard electron. There another electron, as I discussed, that transmission electron. The transmission electron will use in case of transmission electron microscope. Okay. So basic difference is here you are using a transmitted electron beam. So TM is a unique tool that used to characterize crystal structure and microstructure, simultaneously using diffraction and imaging. Earlier case in SEM, you are using only imaging. So here with S imaging mode, you have another mode that is called diffraction mode. The diffraction will produce, it will give you the crystal structure information, and your imaging mode will give you how the sample shape, size, and distribution. So first TM was developed by Ernst Röska and Noll around 1931, that magnification about only 400x. Subsequently, they got Nobel Prize for the discovery in 1986. Noll and Röska awarded Nobel Prize, and first commercial TM developed by Simon in 1939. You can see here, if you the electron even at 1000 kV, 100 kV, if you take that energy, your wavelength is 0.0039 nanometer, and this wavelength is more than sufficiently small to image atoms. Like in XRD, we are using wavelength copper K alpha. The copper K alpha is 1.54 angstrom, which is equivalent to that of the lattice species. But here we are using a wavelength of 0.0039 nanometer, about 0.3 angstrom or even low. So that is sufficient, and image the individual atom can be seen. You can see in 100 kV, you can hide such a low lambda you are going. There are different lenses, imperfection, which what you have in the SEM, or the resolution limit that can be nowadays, overcome by different aberration techniques. So if you see in case of SEM, what you are seeing that electron beam are coming from here on the top side. Detector is in SEM top backside detector here and a second electron detector here. But in case of TM, that it's opposite, like it has to transmit it to the sample surface. You have three phenomena occur here. Mainly, once electron beam falls on the sample, it's transmitted. One beam can be directly transmitted, another is elastically scattered, like it interact, but there is no energy loss. So it is same energy h nu whatever here, that this is h nu here will be same here. But another is inelastic scattering, which will be h nu dash, or the energy that if you see that the energy will be different. That means here lambda and here lambda will be same, but here it may be slightly changes. But that is inelastic scattering. So the another is direct beam. In addition, you can also produce X-rays similar to that of SEM. So your specimen has to be very small thickness, like less than 100 nanometer to transmit the electron beam. So if you see that the three things that image produced by due to the contrast the thickness, like you have a sample, a big sample and small sample, or for example, you have a little bit, 100 nanometer particle and 10 nanometer particle. So that is a thickness difference is there. So electron beam transmitted more easily in 10 nanometer. So that the mass difference or thickness difference will give you the image and produce the diffraction that will use for diffraction analysis. That huge with the EDAX especially to get elemental mapping, and then whatever the inelastic scattering here, that after some energy loss interact and some energy loss and electron beam transmitted, that is used as electron energy loss spectroscopy, yield spectroscopy, that will use again for elemental or chemical information that we will discuss little later. But if you see the STM, the instrumentation part, if you see my image of a TM microscope, laboratory TM, that mostly the top you have an electron gun. You can see schematic diagram of the electron gun here. That is a highly emissive tungsten lab 6 lab 6 or tungsten filament are used as so similar to electron gun source, that similar to that of SEM, but it's here the kinetic energy, the energy of the electron is very high, around 200 keV use here in case of SEM, comparison to 30 to 40 keV in case of SEM. And then you have a various lenses. You have a condenser lenses, a projective aperture, and intermediate lenses. And then you have a sample here, this part. And finally, you have at the bottom, you have a fluorescent screen, that projector, where you're able to see the particles or the image of the sample. So nowadays this image, instead of putting a camera, now the CCD detectors are there, charge coupled detector that will directly take the image. So you can see here you have a condenser, different magnetic lenses there to focus the electron beam, condenser lens, and then you have an objective lens here, and then you have a sample surface, follow the sample surface, then it passes to different objective or intermediate and projector lenses before it comes to the camera or fluorescent screen. So that means you have a content electron source at the top of made up of lab 6 or tungsten, then you have different lenses, and then you have a fluorescent screen at the bottom to collect the image. But if you see, as I told, in TM you have two modes. One is imaging mode, another is diffraction mode. If both the mode, if you see, the difference between the mode mainly depends upon the strength of the intermediate lenses. So the strength of the lenses, how it focus the electron beam. You can see here in the imaging mode, you are at the end, you are getting a whole range, it's getting scanned. But in case of diffraction mode, here you are just scanning a spot, different spots you are scanning. You can see it's coming from the same source, and after coming here in this case, the objective aperture is fixed here. Here above the objective aperture is quite close to this lens. So depending upon that intermediate lens strength, it can focus in such a way that here it will go to whole image scan, here you will able to get spot scan. So mainly the intermediate lens that strength decide that whether it is imaging mode or diffraction mode. So that we generally how to do. So you have a aperture here, that intermediate aperture. So by putting those diffraction aperture, you can control the electron beam in such a way that it will go to the diffraction mode or it will go to the imaging mode. Okay, that is the two things we calculate, we see. So if you see how the diffraction and diffraction pattern and imaging help us to get the information from a TM image. So if you see the electron diffraction pattern, if you see as I discussed in X-ray diffraction is similar to X-ray diffraction here again, that it have to be Bragg's law has to satisfy it. You can see this is a grain structure. In the grain structure, so its electron beam is coming here. Your 2 theta in this case, in case of TM, is very, very low. It's almost flat, like the 2 theta is very, very low. You can two plane I have shown here. One is red plane, another is green plane. When electron beam is falling, you can see that particular lattice plane corresponding to red plane, you are getting a red dot. This is the center of the electron beam. The red dot is from a red plane and green dot is from green plane that I am showing here. So you will get a diffraction pattern. If a single crystal structure, you will get a diffraction pattern like point patterns, dot dot, only dots you will get in case of single crystal. But if the polycrystalline, like 2 or multiple plane is there, you can see 220, 110, 111, or different planes you will able to see depending upon that selected area electron diffraction pattern that we call. So this is the zone which you select to see the diffraction pattern. So what information you will get from the diffraction pattern if you see, but in case of you see a polycrystalline material, this here instead of spot you are getting sharp ring patterns are you are getting. So here there is multiple crystals are there. So each crystal like has a sample, like here this yellow crystal also have 110 plane. This should have 110 plane. So 110 plane is there. So all the crystal have same plane 110, for example, all planes. So what will happen? So because of this all planes, so in that ring you will get 110 plane corresponds to yellow crystal, green, blue, red, all crystal. They will all join together. So then you will get a ring pattern like structure. Similarly, in the higher planes you will be able to see. But here that dots is mainly joining together to get a highly intense ring. That is in case of a particularly in case of a polycrystalline material. But if you see this electron diffraction pattern for amorphous material, there is no proper grain structure is there. There are no long range ordering. So what you will get a diffused ring. So your ring will be diffused like this. You will diffuse ring. But in case of polycrystalline material, you will get a sharp ring. But in single crystal, you will get dot points in case of single crystal, the electron diffraction pattern. So from the diffraction pattern, you can identify your sample is amorphous in nature, all crystalline, or it is a polycrystalline or single crystal. All those information you can get from electron diffraction pattern. So then once you have a electron diffraction pattern, for example, say ring type or a spot type, how do you interpret those electron diffraction pattern? Which ring corresponds to which electron, which plane? How do you identify? For that, you have to use an equation RD equal to L lambda. That means you have discussed that for a UL sphere during X-ray discussion, that wherever the point meets that that 1 by lambda diameter with the reciprocal lattice, that point fall in this 1 by lambda UL sphere, that then only you will get a diffraction spot. So here, as you know, sine theta equal to, I rewrite the lambda equal to 2d sine theta equation as read it in that sine theta equal to lambda by 2d. So here that theta, you can see here 2 theta. So that is so small. So here sine theta will be equivalent to theta. So your lambda equal to 2d theta. So d sine theta will sine theta will be theta here, lambda equal to sine theta. Send the equation R by L. So you can, this is the sample and this is the projector here, the bottom of the projector where your photograph film is taking. This is the L is the camera length, distance from the sample to the projector, that is L, and you have R is the radius of the ring, and this you diffracted beam here. So then R by L, this R by L equal to 2 theta here. Since sine theta will be almost equal to theta, so 2 theta R by L, combining these two equations, you will get RD equal to L lambda. That in the ring structure, so if you use RD equal to lambda L, R is the radius of the ring that you are getting here. Here the radius of the ring, and D the D spacing that you see in XRD, that is spacing. Lambda is the wavelength, and L is the camera constant. You know the L, that camera constant for each TM, that distance you can measure, that L camera length, and then you have a lambda is fixed about 0.0025 nanometer in case of 200 keV electron microscope, and then R is ring diameter you can measure, then D spacing you can easily calculate. But here in case of TM, you know, the lambda is the theta is here small, very small, and lambda is also too small. Because of that, your 1 by lambda, in case of a lambda is equal to 0.0025 nanometer in case of, you know, this copper, in case of in case of this TM, so that 1 by lambda will be very small, and because of that your UL sphere is almost looks like flat. So because of that, many points can be matched. So electron diffraction will give you much more information than X-ray diffraction, but the interpretation is quite difficult. That's why electron diffraction is not gain much more familiarity as compared to X-ray diffraction. Similarly, you can see I have shown here ring pattern. Once you measure the ring pattern, that you can able to identify each in each spot what is the, you can measure that 1 by lambda, that here that this spacing, and you use that equation RD equal to L lambda, you can calculate each plane. But nowadays this is the thing, the RD equal L lambda we are discussing. That case my scale is in nanometer, like 5 nanometer, 1 nanometer in the TM, like old image that you get in a photographic film. But nowadays, that if you see that most of the TM giving inverse scale, 5 upon 1 by nanometer, when that 1 by nanometer, when the scale is there, this equation is taken care by the instrument. So you just measure the diameter of the ring, like one bright spot you take and opposite bright spot, just you measure the diameter and half of it, you will get the radius. Then if you do 1 by r, that is nothing but your D spacing. So why that will directly you get, since the reciprocal lattice 1 by n nanometer is given, just you measure the diameter and half of it will be your first plane, then second plane, third plane you can calculate. In case of relation, you can apply all this relation, simple cubic 1 by d square equation is n by a square. So by using FCC, BCC, you can calculate that lattice parameter also from this equation. But if you have a spot pattern, electron diffraction that looks like a spot, in the spot pattern, the interpretation is little difficult. Here, like this is the center point you have to identify first. That is that what is that HK, H1, K1, L1, or H2, K2, L2 is another plane here. So what will that do? This is the spot you will find out, and then these two, if you identify, this one is your G1 and G2, then HKL value of this one will be G1 plus G. You just vector sum of that two. Like for example, this is the center 0, 0, 1, you identify, this is 1, 1, 0, 1 bar 1, 0, this is 0, 2, 0, then this will be 1 bar 1 plus 2 plus 1, 3 and 0. That is 1 bar 3, 0 will be this spot. And similarly, you can calculate this spot, all these spot. You can calculate that the center beam, this is -1, 1, 0. This will be minus 1, -1, 0. Then this is a 2, 0, 0, -2, 0. All those planes can be identified by measuring the distance of the diffracted spot from the central spot. You can able to identify the scanning that all planes in case of an electron diffraction pattern of a single crystals. So far I have discussed about the diffraction pattern. We'll take 2-3 minute break, and then we'll discuss the imaging part of the electron microscope. From till this you can ask right now, or you can raise your question in the chat box. ऑन करना पड़ेगा, ऑफ किया है।
एक मिनट सर, मेरा आएगा।
पर ना,
मेरा आएगा ना।
अच्छा आपका है। शेयर कर। Okay, so far we have discussed about how electron diffraction pattern helps in interpretation of information, what information can get. Mostly in electron diffraction pattern we can suggest whether my material is amorphous, crystalline, and if it is the amorphous or crystalline, we can also identify in case of or is a single crystal or polycrystalline material that you can identify, and then you can interpret each planes you can identify, and based on that you can interpret our crystal structure and whether the sample is formed or not, that can be identified by electron diffraction. And another mode of electron microscope, that especially transmission electron microscope, is imaging. So the imaging is the same way how that of SEM, but here the transmitted beam is using. Here the image of the specimen is formed selectively, allowing only transmitted beam. That only transmitted beam will be allowed. That will be give you a bright field image, or there is a diffracted beam you can allow, that will give a dark field image. So in case of image, you get two types of image you will get. One is a bright field image, and another is a dark field image. And the origin of the image contrast with the variation of intensities of transmitted beam or diffracted beam due to the thickness of the material, that means due to the jet contrast. Depending upon the thickness of the material, like you have a sample here, like in this side, like this type of sample, for example, here thickness is less, here thickness is large. So depending upon this thickness and this thickness, you will able to get the image quality. Electron beam transmission here will be easy as compared to here, it will be take longer time. So because of that jet value, that or the thickness value, you will get the how the electron beam is transmitted between this, that will give you the image. So first thing, you have a mass thickness contrast. The contrast appear in the image due to the difference in the inherent scattering from the sample. Like with a thick sample and a bulk, you might have seen sometimes that when you see a nanoparticles, you somewhere you see dark patches. That's mainly due to multiple particles, aggregated together, and the electron beam is now transmitting to that aggregates. Then you'll get very dark image. So that will be a thickness, and then you have a jet contrast, high resolution the version that you can get in the jet contrast. You have tungsten, and you take silicon or gold. That those type of they have a see atomic number difference, because of that the low jet material electron can easily passes through, or high jet it takes more time or it's not easily passed. So depending on the mass thickness contrast, you'll get an image. And similarly, you have a diffraction contrast, that in crystalline material you have a diffraction occurs. Then you have a diffraction, then you can take the diffracted beam also to get the information about the crystallographic information. And you have a phase contrast image, that is a high resolution image where both directly that transmitted beam and diffracted beam, both the beams coming together to get a phase contrast image, where you can able to see the atoms or defects inside the my sample, that you can able to see in case of phase contrast. So we'll discuss one by one. So first, coming into the bright field image formation, how does the bright field? And here you can see that this is the objective, this is the some sample, and after interacting with incident electron beam falling on the sample and going through the objective lenses, you can see here this is the direct beam is coming here. This is the direct beam after interacting with the sample, and this dotted line is your diffracted beam. So the diffracted beam is stopped here by the objective aperture. Only direct beam which coming directly after interacting, that is passing through the small hole here, objective aperture, and falling in the photographic film to get the image here. So this is the bright field image. In the bright field image, that is direct beam is coming here, the center focused. So direct beam is coming here. The diffracted, what is the diffracted beam? After falling here, this beam is, you can see diffracted angle 2 theta. So these diffracted beams are, you are separating them and you are getting the image is bright field image. But in case of dark field image, what you can see that direct beam is getting stopped here. You can see the direct beam is coming here. The direct beam is getting stopped by the objective aperture, and that indirect beam or the diffracted beam with the angle 2 theta, that beam is passing through this hole, and that the objective aperture, you get a image that is a dark field image. In case of bright field image, what you see here, you will see that if you see the TM image, that sample will looks like dark, and all the other things will be brighter. Sample will be your darker gray color. But in case of this bright field image, you will see mostly it used for grain structure analysis. You will get bright spots. These bright spots will be your crystals, and your background will be dark in this case. That is called dark field image. So it's mostly your diffracted beam you are collecting here. The diffracted beam, the direct beam is getting stopped here. So that is the dark field image. And dark field image, again, two types. That one is center dark field and that is dirty dark field. You can see here center dark field, you can see here some incident beam is falling parallel from the top surface, is perpendicularly is forming to the sample surface, then getting diffracted here. So diffraction beam is getting collected to get the images passing through the aperture lens. But here center dark field, you can see instead of using a beam electron perpendicular, the electron beam is falling at an angle, some angle. Then after diffraction, after diffraction here, that it's getting perpendicular. You can see. So in such a way that beam is aligned to the sample surface, the diffracted beam will fall into the objective lens. Here it will be, if you see this angle will be perpendicular, then it will be centered focus. So here it's not centered. That is called dirty dark field. If you center dark field, you will get on axis dark field. You will get better, crystal structure. Crystals you can see here. So if you see the image difference, that as I told, that there is a bright field image. In case of I am discussing about bright field image now, you have a mass construct. If you see that, you can see that I have taken a material. This side, left side is low Z, and this side is high Z. In low Z, you can see the image here. The electron beam is getting transmitted more easily. So you are getting this type of structure. In the high Z material, electron beam is going less. So that's why your just image, your whatever image you are getting. So being image is mostly transmitted to this zone. Here it is image will be that this image is creating So the image is creating that, you can see here, depending upon the Z contrast. So image is getting, opposite image you are getting here. So whatever you are getting, so depending upon the low Z, your high Z, you will get that schematic representation you will be able to see. And the contrast here is a function of Z, that is mass or density of the material. The more the scattering with high Z material, the scattering will be more, so transmission will be less. And thickness, more scattering with higher thickness, that you will be able to see. Then in case of polymer sample, amorphous or biological samples, you can able to see the thickness. You can see I have shown an image of Fe3O4 coated with silica sample SiO2. You can see your core is Fe3O4 dark, and silica cell you can able to see the cell here, outer side the cell here. So cell, the silicon is cell, and this center is your iron. So if you see the atomic mass of iron and silica, so there is a drastic difference. So because of the Z value, you can easily see the core cell structure in case of using a mass construct, mostly bright field bright field TM image. You can able to see that the TM imaging. Similarly, in the dark field, you can see here that the dark the white patches you are able to see. This is a bright field image. You can the samples are looks like dark, and your background is bright. Your background is this is bright and this is dark here. But here you can see background is dark and the spots, bright spots are there. So these bright spots are nothing but grain. If you want to see in a polymer matrix, in a polymer, you have put some grains of zinc oxide or nickel or some grain nanoparticles. So those who want to see how the nanoparticles is getting distributed in my sample, in my amorphous polymer matrix, you can take such a diffraction pattern, a center diffraction pattern with a dark field imaging. You'll be able to see the image you will able to see in case of and by dark field image. But in addition to TM, there is another version is attached that scanning TM is used. That is called that you can combine like STEM. That you have a SCM, like it's similar to SCM and TM combination. You can see you have a scanning transmission electron microscope here. So you have a raster scan on the top surface like SCM. That raster scan will be scan the sample surface. Here is parallel beam used here, but you have a scanning beam you are using. So because of a raster scan, you will able to both you can get a bright scanning SCM type image you will also get. Like here, in case of some of the information, you can see here how the individual precipitation or grains are there. So those information is not clearly visible normal TM. If you combine with STM scanning TM, so then you'll able to see both better image contrast you will able to get, and you will able to do for the EDS analysis, element analysis you can do in STM. You can do an electron energy loss spectroscopy yields by measuring the energy of the electron beam. You can interpret whether it's a coordination number, oxidation number like EXAPS and illness. You'll able to get all those information. So here in STM that I have shown here, you can get the composition analysis. You can see that this is a zinc and cobalt, that how this is distributed in cobalt of sample. You can see cobalt, zinc. This copper is mainly coming from the TM grid that you have used the copper grid that you will just a minute. Just excuse me. Yeah, you can get that different. As you know that you have a copper grids are made up of various maze. Most of you see the copper grids. They have small squares. In this square, you have a carbon coating on the top surface. This type of carbon coating on the carbon coating, you put your dropcast or sample solution, and then this copper signal or carbon signal will mainly comes from the copper grid and carbon coating. In addition to that, you get the cobalt and zinc signal is coming here, and you want to see how this distribution of my zinc and cobalt. If you take a line scan across the sample and you scan from one end to the other end, you will see the spectral scan, the distribution. You imagine a sphere. In a sphere, when the line is, when the electron beam is passing through the center, it interacting many atoms. When it the surface interacting less atoms. So that means you have a profile, the path length is moving, is quite large in case of center, so it will get a hemispherical structure. If this is its distribution is hemisphere, that means your particle is uniformly distributed inside the nanoparticle that you can get. And you can see here by line scan also, you can see here this one hemisphere, here it is my iron is distributed, not iron, this is a I think that cobalt is distributed. This the distributed zinc. Sorry, zinc is distributed uniformly. Whereas the iron, you can see here it is somewhere it is dense, it is somewhere less. You can see it's not a hemisphere. That means it's a Fe3O4 zinc oxide sample, or it's formed by aggregates of nanoparticles. Inside that, you have many iron oxide. Fe3O4 has been embedded. You can see how these Fe3O4 distributed by using spectral mapping. But if, as I told, if you have a core cell structure, that core cell structure can be identified by SEA, by TM, by Z constant. If you have a difference in silica and iron, that Z difference is very high. But if you go for a Z difference almost similar, like nickel and cobalt, or iron and this this platinum, PDPT, this PDPT or NiCO, that Z value is very, very small. So there you can't able to see any difference in normal STM microscope because the contrast will be same, the electron beam transmission capacity will be same both those cases. So there you have to go for STM. So you can see here, this is a palladium platinum by electron mapping image. By using electron mapping, this is my how my palladium is mapping, how platinum is mapping. Then I combinedly I can see what is the K alpha distribution of platinum to get that structure. This is another example where cobalt nickel alloy is formed. You can see here initially you have a core cell structure and then you have a distributed heat treatment higher temperature. The whole thing green and red will be combined. You will get a yellow signal. You can see here at low temperature, you can see there is a red and yellow and green and yellow signal, red signal there. When high temperature 600 degrees centigrade, you can see almost a convert to yellow signal. That means that now it is getting from a core cell structure to a alloy system which is uniformly distributed, NiCO alloy. So the material having similar Z can be identified by TM elemental mapping. So this is that can be possible. In addition, as I discussed, there is electron energy loss spectroscopy. That yield spectroscopy will be huge. That after interacting, electron beam was transmitted to the sample surface. When due to interaction, it will lose some energy. So it lose some energy. So and then electron beam will be transmitted. That inelastic transmitted electron beam. So once that energy loss, so there is one is zero loss, no energy loss will take place. Then is a low energy loss. There's a core loss, high energy loss. You can see starting about much higher than 100 eV. So based on that, you get a absorption peak. You will get some near edge band edge absorption peak from that. That electron energy loss spectroscopy that have two parts. One is electron energy loss near edge structure illness and extended energy loss that exlapse like EXAPS and EXNES in case of X-ray absorption spectroscopy. So this will give you illness will give oxidation state and EXLAPS will give you ELFS will give you coordination number or interatomic distance. That means from TM you can also get the information about oxidation state and coordination number based on the electron energy loss spectroscopy. So after electron beam interacting the sample surface, how much energy is lost, that energy can be identified. You can get the near edge structure and extended structure to identify whether my spectra or the information can get like oxidation like the titanium Ti3 plus Ti4 plus. You can see you are getting your peak, how the peak difference from their oxidation state you can calculate. You can also combine STM with yields. If you combine STM scanning TM with yields, you can able to get element analysis. You can see here you will get aluminum mapping, titanium mapping, and oxygen mapping. And you can combine to see it's a circuit diagram that you can see by yield spectra. That is possible. And similarly, another things that is there in case of TM is high resolution microscopy, high resolution transmission electron microscopy. So far, I discussed diffraction pattern, then bright field, dark field image. In case of bright field, you have a direct beam is coming. In case of dark field, you have a diffracted beam is coming into play, and you have in STEM, you have the raster scanner that is scanning. In case of yield spectra, you have an electron beam energy loss is coming, how much energy is getting lost. From there, you can get that information about oxidation state and that near edge and extended edge structure where you get the information about oxidation state and coordination number. The fourth thing is there, that is that high resolution TM that use both in transmitted beam and diffraction. You can see the incident beam and then the sample is here, it's falling parallelly on the sample surface. Then you have a diffracted beam and transmitted beam, both are coming. So they will interfere each other, and because of the interference, now you will get a phase contrast, a high resolution image. That means you can see here your aperture is such a big it will take both. You can see here both direct beam. This is direct beam that is coming on the sample surface. This is diffracted beam that is also coming onto the sample surface. So the direct diffracted beam, this is the direct beam. So both diffracted and direct beam both coming into picture in case of high resolution, that is called phase contrast image. Here you will get the thickness, and depending upon the operating condition, you will and the thickness of the material, you will able to properly focus to get the HRTM image. I have shown some example. If you see here, this is some of the zinc oxide, that manganese of zinc oxide. These lines are nothing but the lattice planes that you are able to see. You can get the interplanar distance by measuring the length. You can just that you can use that DM3 software in TM, or if you normally use images software, you can draw a straight line passing through this, and from this straight line, if the lines are like going this, so you will get this type of these peaks you will get, and that this to this distance, this to this distance, this to this distance, that will be your lattice spacing. So individual one is difficult to measure. You take a large line, big line, and measure the whole length and number of peaks you are getting. You just divide, average out, and you'll get the lattice spacing. And then this is the diffraction pattern that you are getting, so that it can be identified from a single plane. Those things can be possible. You can see this is grain 1, grain 2, grain 3 grains are there. How these 3 grains are arranged, that is, you can see these are the atoms, how these atoms are hexagonally arranged. In case of zinc oxide, is a Ujite structure, that is mostly hexagonal, hexagonal structure, that atoms are arranged in hexagonal plane. So that you can identify here, and in between 1, 2, 3, how the atoms are arranged, that can be identified. You can see here. So this is the taken some FFT Fourier transform. From this image, you will go for a Fourier transform, and then for inverse. This is the IFFT, inverse Fourier transform. You will get the original better quality. You can see here, some planes are clearly passing through, and particularly this zone, you can see one plane is coming, and here it is bifurcated into 2 planes. So it's more visible. You can see here this plane. You can one plane is going like this, another is going here, another is going here. You can see there is in between, there is a defects is there. So that defect plane, all those dislocation can be identified in case of TM. And even you have a stacking fault, that you can see here, these are the individual atoms are there. These atoms should go in a straight line. So instead of straight, it's going some wavy structure. You can say I have drawn a straight line here, so it should go like this. Instead of that, it's deviate from the arrangement, is deviate. So that is nothing but your stacking fault. So those stacking fault, atomic rearrangement can be seen in HRTM image. But if you have a biological samples, those biological samples is not possible to do in normal TM. As in normal TM, your energy is 200 keV, is much high energy, whereas all your biological sample will be completely destroyed, completely burned out. Or if a polymer coating or organic material, those things will not possible to see in normal TM image. For that, you have to go like environmental SEM. We have a cryo TM. Cryo means low temperature, cryo. So you have a cryo TM here. In that cryo TM, so you are freezing the structure at liquid nitrogen or liquid methane temperature at such a low temperature. It will biological structure will freeze, and you can able to, so you can see this is the liposome structure, all the liposomes. You can see the bilayer inside here. You can see that bilayer liposomes, all those images. You can have multi-layer bilayer, can able to see. This is a cryo of the micelles. Micelles, the surfactant assemble, that depending upon the head and face alignment, they will either reverse micelle or is a normal micelle. Those micelle structure you can able to see. This is a cryo V, this is a marine virus. That virus structure you can able to see by using the scan here. In case of cryo TM, instead of 200 keV, this is 120 keV. The energy is very, very low. In case of this, at 120 keV, the most of the structure that can be preserved, and a low power electron beams had to used here. Cryo EM is advanced through direct electron detector device. That means here the electron interaction is less in case of this cryo mode, so you'll be able to get the bacterial or virus structure. But if now you're coming to a sample preparation, if you see that you have a nanoparticle, you have to disperse in a suitable solvent like methanol, ethanol, or water. But in water it will take more time for the vacuum to reach but better to use a ethanol, or isopropanol is the best solvent. You disperse in isopropanol, then just put 1 drop on TM grid directly. You take your TM grid on a filter paper like Hartmann filter paper and put your TM grid and dropcast your sample on that one directly, one on the near to the grid on the filter paper. So like if you have a grid here, this is the grid on the filter paper. So 1 drop you directly put here, another drop on the filter paper near to this you put. So that will be sucked here. So you don't put large quantity, and your solution has to be translucent, not turbid. It's just that if it's reddish color sample, slightly translucent reddish will be fine. Which more color is highly aggregated, that concentrated, then your particle will be aggregated. Instead of getting good image, you will get a cluster. You will not identify the each nanoparticle. The sample preparation is very, very important in case of TM. In biological sample, you have to go through many process. Like you have to first you have to wash it like proper sample surface sample has to be properly washed, and then it has to be fixed with some resin that you have to take that in the resin you have to fix the epoxy resin. Then you have to cross section ultra microtomy, do fine cross section of about 90 angstrom to 90 nanometer around. In that cross section you have to put on the TM grid, and you'll be able to see this whatever the like inside the cell, whether nanoparticle is going to nucleus or cytoplasm. Those information you can get. You have to follow all this whole process. Like you have to fixation you have to do with high Z material, uranyl Z, tannic acid, or your lead acetate with high Z material. Like then you have to stain it, then you have to put it. Like another one is a negative staining sample, that is for micelles or vesicle. So those things, normal TM, it will be borne out. So what you do, you have a micelles here, like this is a micelles, here is form a spherical aggregate like this. You put a uranyl acetate or lead acetate high Z material, so that will soak on these micelles, and though this whole micelles will bond out, but the position of the uranyl acetate will retain. You will see the from the uranyl acetate or lead acetate position, you can identify the micelles information. That is called negative scanning. But if you have a metallurgical sample, then you have to go for slight thickness. You have to do milling, ion millings. Like you have a bulk sample, then you have to cut it to small mechanical lapping. You have to cut it small. Then ultrasonic cut, you have to do. You have to take a very, very small thickness. You have to get, and then by dimpling or manual lapping, you will get do a very, very slight thickness of 100 nanometer or so. Grind to very, very small, grind to 100 micron, and so then dimple to 10 to 20 micron. Then you have to go for iron milling, where it will leach out to very, very small thickness you'll get. And now you put in the TM grid to see the structure, the top view. But the cross-sectional view, you have to cut a cross section with the layer structure. From then you have to grind, you have to cut it in such a way by using different type of iron beam cutter, and then you'll get this type of TM grid type structure. You'll get at the center you have to iron mill to get a very very such a low thickness. You can see here electron beam can easily transmit it to see the whether there is a grain boundary, whether there is a some information about precipitation. All those information you will get. So basically in TM you will get that imaging where bright field, dark field is there. You can get the image, shape, size information as well as crystallography information by diffraction pattern, and then you will get in addition you will get information about defects, lattice plane, dislocation by using HRTM, or you want to see the how the atomic arrangement, all those information by HRTM. So I'll just take another 10 minutes to discuss about atomic force microscopy. This is slightly different than that of TM, but in normal SEM TM mostly will get a 2D image. Then after reconstructing, you can get a 3D image from a from TM, but normally 2D. But in atomic force microscope, here force between atoms and tip. You have a sample layer here, then you have a tip. This is the scanner that the tips. This is the probe, and this is the sample. And from this probe to sample interaction, that the force between these we measure. It's a part of SPM category microscope, that scanning probe microscopy. That's two types. One is scanning tunneling microscopy, which measure current between these tips and the sample surface, and atomic force microscopy that measure force between these two. Here it is gives mostly 3D image you can get easily, and here it all these things based on Young's law, that is force F equal to kx, that minus kx, that force constant F equal to minus k into x, that equation Hooke's law. It is depending on the force you can find out. You have a spring here that after interacting with this, that spring constant k, and that x is the displacement. From there you will get the atomic force microscope. If you see the FM was high resolution, you get 1,000 times better than that optical microscope. You can able to see 10 nanometer sharp probe up to 10 nanometer if you use. You can short distance, so the nanometer size sample you can able to see. This is some of the history that I am not going to discuss. And mostly if you see here, this is the SEM image, it's the FM image. In the FM you have a sample tip on the surface, then you have a sample here, you have a sample stage and the sample kept here, and below that you have a different type of piezo transmitter to move the sample surface, and you will get that FM image. You can see you have a sample, the sample stage. This is the sample stage, XYZ scanner that is, and you have a sample on the top of this. You have a sample, and then you have a cantilever kept here. That cantilever with a sharp tip. The tip is mostly made of silicon nitride type semiconductor material, and sample stage is a piezoelectric material, barium, palladium, barium titanate, and then that is a piezoelectric metal, but you have to move up and down that scanner, and then once you applied this some particular force, so what will happen? It will scan the sample surface. Then a laser is coming here and going to the detector. So depending upon the movement, it's moving like this. It's up and down moving. So it will detect that the voltage generated between them, which will later converted to the image. So here you have a creep measure parts, who are mainly used to analyze just to analyze the polymeric materials, thin films, nanoparticles, glass, semiconductor, metal, ceramic, biological material, everything you detect. You don't need a high vacuum. It can be done in the room ambient condition, and not much sample preparation here. Your main thing is a piezoelectric crystal, that is a scanner, and then you have a probe, cantilever is there, and then its display is going. Just going again and again. No, the display is going. Okay. Then you have a beam deflection. Then you have a beam deflection. The laser beam is falling, it going to the detector. These are three main component. If you see here, this is my sample. On the sample, you have like humps are there. Like this type of my sample is this type of structure. When the tips has moved here, you can see my force is same. My distance is also same. The tip is going closer here to sample surface. When there is a hump, my tip is going up. So tip is moving up and down, but the force the displacement is same, but my tip is going, that is measuring that what is the different force that can be measured. Initially the tip at position A, the material surface, let the force is F. Next the tip move to position B, which is higher height than A. So feedback loop that used, so the loop that will maintain the fixed force, the force will remain constant, and it will measure the force between them. So you can see here, this is my sample, here will be my sample. On the sample, my cantilever is there. My cantilever is moving up and down depending upon this way it's moving, depending upon the position depending upon the position of the this humps or the surface morphology, it will move up and down. Then you have a loop here, feedback loop, A, B, C, D loops. So my light is falling on the tip surface, and then it's going back to a photodetector where it's reflecting back to my detector A, B, C, D, the photodiode. So here you can see whether this position is going to A, B, falling at A, B, or falling on C, D. So that is mainly deciding how the force is generating and what is the displacement, that you will measure it based on Hooke's law of displacement to measure this. And you can see the different working mode. You have a three type of working mode. One is contact mode, non-contact mode. Mainly the contact mode, tips made directly contact. You can see there is a force versus this. If you see the distance, then you have a contact mode that is mostly here, and you have a tapping mode, and you have a repulsive zone, you have a non-contact mode. And attractive and repulsive in that it depends. So contact mode is tip makes soft physical contact, that mostly in case of repulsive zone. There are some technical problems. So if you see that mostly three types of mode, that one is contact mode where sample is directly contact with the tip, and there is a non-contact mode, there is an attractive region here. The sample will not directly contact, but about a distance of 0.5 to 2 nanometers, but probe to here that is slightly gap between the sample, and then the force is your 2200 nanometer. And then you have a tapping mode that is just tap the, if you have a rough surface here, the tip will just tap and go up, tap and go up like this, tap, and then it will go up like that, tapping mode. So more maps topography image you will get mostly in all this case. In this mode, the cantilever is oscillating close to the resonance frequency, and the separation distance about 0.1 to 10 nanometer. So you'll get mostly topographic image in all these contact mode, non-contact mode, or tapping mode. So if you see the sample preparation, if you see that is quite easy, that STM, that or AFM sample preparation is involved choosing the substrate and then attaching the sample to the substrate with optimizing the scan parameter. Here you can take a mica for negatively charged, where you can use DNA, protein. Those are illustrating interaction between them. You can take on the mica surface, or you can proteins. You can also take a hydrophobic graphite substrate. You can take a glass cover seal on which protein or cells you can mount, or you can mount your sample, or a polystyrene petri dish on which cells can be directly attached. So the quantity of sample preparation is the key factor for the quality results. So sample can be directly drop casted, or it can be spin coated on the sample. So you see, FM has a wide range of application. It can use resolution of nanoscale topographic image of the surface, polymer, thin film, nanomaterials, DNA molecules, protein adsorption, crystal growth, living cells, adsorbed biomaterials on the surface, dental implants, all those things. Some information you can get from AFM. Then AFM can be used to measure thickness of the thin film. Like depending, you can also measure the roughness, from where you can calculate the thickness of the material, surface roughness. In addition of topographic measurement, AFM can use to get information about surface properties like stiffness, hardness, elasticity, friction, all those parameters you can also get. AFM technique can be modified to measure the conducting nature, that is conducting AFM, that is called EFM, electric force AFM, or magnetic force you can use. Mostly in the AFM we use van der Waals force. We measure the van der Waals attractive force between the sample surface and the probe in case of atomic force microscope. But in case of conducting sample, where you can EFM use, that electric force microscope can be used. If magnetic material is there, you can use magnetic properties, the magnetic force of attraction, that will be magnetic force microscopy. MFM can be used. In biology, AFM can many applications include imaging of biomolecules, antibody-antigen interaction. You can see the binding force. You can find out ligand receptor binding mechanism or binding force of complementary DNA standard, like two DNA standard, the double helical structure, all those complementary information you can get. You can see the AFM imaging. This is a topographic imaging of a HOPG, highly oriented pyrolytic graphite. You can see how the hexagonal arrangement is there, what is the atomic, each distance, that atom distance you can able to measure. This is a mouse fibroblast, is the cells that you can see here. This sample is a block copolymer. This polymer alignment, that arrangement you can able to see in this nanofiber, the coating, this fibrous nanostructure, wire-like structure, that image you can get. You can quantum dots like cadmium sulfide is a quantum dots. You can measure that quantum dots. You can gold film on ceramic grain. This is a ceramic grain on which is the red color gold, pink color gold film has grown. That you can see. This is a dental implant. On the surface of that implant you can able to get. This is the butterfly wing. You can see that different wings are how they interconnected, all those information. But AFM can be possible from the most important thing. In case of TM or SEM, what you are seeing, you have a nanometer region you are able to see. But here you can able to see from micrometer to nanometer to angstrom level, you can able to see in case of AFM. Also you can get a 3D image. If you see, this is a topograph HOPG, that how this 3D humps, that you can see how that they are arranged in 3 dimensions. You can able to see. This is geobacter, gold film, that bacterium that growth on the gold film, that bacterial growth that you can see from the 3D imaging. That means AFM imaging, you have after scanner that scan the surface, then also you have a height profiling can be possible. You can also get a 2D versus 3D image. You can see in case of, this is a SEM image. In SEM image, you can see this is a top surface, this is a fractured surface. You can see here the hexagonal arrangement of atoms here, hexagonally arranged, how the atoms are here hexagonally arranged. Here is you see the cubic arrangement of atom in cubic arrangement between the atoms, between the 100 plane, but here it is hexagonal arrangement. All those information you can get. That in 3D image you can see how the hexagonally they are aligned with each other. Those 3D image you can able to get from a 2D to 3D image. If you see, the compare the AFM to SEM and TM, sample preparation in case of AFM is little, almost none, but in SEM you have to do little sampling. But if a TM, you have to do lot of sampling. That's important. Sample preparation main important for TM microscope. Resolution wise, AFM and TM, you can go up to same, and the cost wise, this is a high cost TM, whereas AFM is much lower cost. Ambient temperature you can do it, and you don't need a vacuum, and you have a 3-dimensional image you will get in case of directly. But in SEM TM, it's difficult to get direct 3D image, and maximum field of view, that is a micrometer, you can able to see also. And you don't need like conductive or insulating sample, both AFM can be done. But SEM, TM, you have to make it a conducting sample if it is non-conducting. So if you see the 3 microscopic technique today you discussed, one is SEM, one is TM, and AFM. If you see the take-home message of this today's class, that mainly SEM will give you topography, morphology, and composition. Like you can see by using backscatter or secondary electron, you can see topographic and morphology, or the X-ray is coming out, the EDAX analysis, you can get the composition. You can also get the focused ion beam FIB. If you combine with SEM, you will able to see the crystallographic information. For biological sample, you have a ESEM technology. In case of TM, you can go to atomic resolution. In AFM also you can get atomic resolution imaging. but in TM, in addition, you will get elemental mapping using EDAX specialty in both SEM and TM, oxidation state and bonding energy, you can bind bonding information, ELS, ELC, electron energy loss spectroscopy, though I have not discussed much detail, but in yield spectroscopy, you have two part. That is, one is near band edge, another is extended band edge. From there, you get oxidation state and coordination number like the X-ray absorption fine structure spectroscopy. It is equivalent to that of EXAPS and yields. Almost either electron beam is used. Here it is X-ray is used in that case. And then you can get the structural crystal information from electron diffraction pattern. You can get crystal structure information inside the defect, dislocation, stacking fault, all those information. You can get TM, and you have a cryo TM for biological sample, and you have a STM mode that will be useful for, combined with that. You see the similar same Z material, how the zinc and nickel, if both are, or you have a like palladium PT core cell structure, or nickel Fe cobalt, that alloy system, all those these. And in case of AFM, atomic microscope, and by measuring the force among team and team by tip and sample surface, you will get that atomic force microscopy. And in case of tunneling microscopy, scanning tunneling microscope, that measure the electron, the tunneling current, and that current will measure. This the AFM is part of SPM category, scanning probe microscopy. In addition, you have a MFM for magnetic force microscopy. For electro force microscopy, you have electric force microscopy is there. EFM is there. So mainly we discuss electron microscopy, that is the bulk, that is the small nanoparticle characterization. In next class, we will see how here it give the inside morphology of this thing mostly. So how the surface morphology, like that interface structure, can be measured using XPS and secondary electron microscopy, that we will discuss in next class. If there is any question, you can ask right now, or you can also mail. Sharing screen. Is there any questions? Okay, if not, then we'll meet on Wednesday for the last class of mine, the module 2, that is on that X-ray photoelectron spectroscopy and secondary ion mass spectroscopy, that's to the surface characterization techniques.